Thank you. All right, so today I'm going to be presenting some modeling results that we're doing for kind of a case that's been brought up a couple times already where it's been mentioned that once you start adding these impurities to water, once you start freezing it out, you kind of start separating the liquidus and the solidus, and you can kind of get this stable phase of partial melt that's kind of this mush or slurry. And so we've kind of been looking at that and taking some hints from some sea ice modeling that's been done to kind of simulate how this kind of like slush will evolve. So the idea here kind of comes from the magmatic system where once you start cooling down melt, it starts to solidify and it'll kind of fractionally crystallize and you'll have this sedimentation. And so you have this kind of porous slushy layer with this kind of ever-evolving pore fluid in here. And the same thing can happen for oceanic systems. So we see this down in Antarctica, North Pole, things like that, where once you start cooling down a brine, it will fractionally crystallize and you end up with this same kind of partial melt here that's filled with this interstitial pore fluid. And this is a really nice photo of laboratory-grown sea ice where you have this kind of pure fluid down here and a solid up here. And here you get these brine channels that form in this melt. And there's definitely like a gradient that's going from more pore fluid down here to less pore fluid up here. And we want to model that. And so why is that important? So if you treat ice as this just kind of like solid block that doesn't have this kind of two-phase behavior, then you're just going to have conductive heat transport and you're not going to be able to trap any solutes. And obviously that doesn't even work for the pure ice case when you put ice cubes in a freezer or something like that. But once you get this two-phase behavior, then you can start thinking about conductive and convective transport, and you can start thinking about how you're going to trap these solutes in these pore spaces, things like that. And we're going to argue that it really can change the entire thermal behavior of this boundary between the ice and the ocean, because there's such a difference between the specific heat and the conductivity between the fluid and the ice in this. So even at small fractions, you're going to have some effect. So one of the big issues that we're working with is that the models that we're running are pretty small scale, but we're interested in large scale features like all of the poles, like long-term climate modeling, things like that, or an entire ice shelf. And so that's kind of what we're focusing at here, is how this can relate to some more planetary applications. And so the idea for the model is that we're using just continuum, basically reactive transport modeling in porous media. And so it's called mushy layer theory, which basically tracks conservation of mass for salt in your pores and also conservation of heat. It's a continuum model, and then we use an enthalpy method that basically tracks the solid fraction throughout the model. It's a one-dimensional finite difference model. We also wanted to take into account that you can get this convective overturn. So as on top of just having the solutes and the heat diffuse through, you also have this definite convective overturn, where when you're rejecting brine, when you're rejecting salt, as you're freezing it out, it gets trapped in these kind of pore spaces and channels, and eventually will become gravitationally unstable and convect down. And so because it's a 1D model, we're using a parameterization that's frequently used for sea ice that basically is just relating a flux down into the underlying ocean based on that. And so we wanted to see, does it work for sea ice? Want to validate the model, and so basically you can turn this model on, and as time goes along, you can track the temperature, you can track your liquid fraction, the overall salinity. If you run this long enough, you can basically compare this and take a vertical slice, so it's like taking a virtual ice core essentially, and you compare the total, the bulk salinity values of the model, which is the dashed to solid line, and then the solid line down here, to actual ice core values. So people have gone out and you can measure the salinity. And that's the red here, and then the active layer down here, and they match up pretty well. So we're pretty confident that the physics that are happening in this model are pretty accurate. For the Europa environment, we kind of use as a test bed. We had to do some different chemistry. So when we're calculating these, how the brine's behaving and the interaction between the ice and the liquid, there's pretty well-known liquidus lines for seawater, but not so much for Europa. So we took some theoretical chemistries from Zolotov and Schock 2001, and then using the freeze chem equilibrium chemistry model, kind of wrote a new code that can calculate some new liquidus curves for these unique chemistries. So basically now we have a model that you can basically throw whatever chemistry that you want at it. It'll go through different concentrations and different temperatures and basically produce you a quadratic line for the liquidus, which we can throw into our model. So the big goal here, I think, for me is trying to take these small scale models and produce these constitutive equations that can give you ideas for things like the chemistry of the ice on a large scale. So instead of having to actually go through and explicitly model a whole ice shell, you can come up with these relationships between your environmental parameters and what the ice is going to look like. So we've done this for a bunch of different compositions for the Europa case, where we basically run this multi-phase reactive transport model at different layers in Europa's ice shell, and then we'll fit curves to basically the salinity profiles that are produced at these different layers. And if we assume just a conductive profile for simplicity, we can match that to a temperature gradient. So basically, you're coming up with these constitutive equations that can say, we can know how much salt is going to get trapped in the ice based on the local thermal environment, which can be helpful for things like when you're freezing out liquid water bodies on any of these like putatively cryovolcanic locations, whether it's dikes or sills or lenses or something like that. The nice thing about this is that they're pretty nice curves. They're linear at low gradients, and then they depart from there. The nice thing about that is we're writing up a paper. If you solve a simplified model that's kind of close to the Stefan problem, it's in between like a pure solid freezing and the full mushy layer equations we're working at. You can reproduce these functional forms. So we're confident that these linear to just 1 over kind of temperature gradient curves are pretty good. And so we kind of just keep ramping up, and we can do it for different salinities. We've done it for kind of like a baseline. We've done it for something that was listed as an upper limit for the magnetometer data. And so we get these profiles that basically say we can calculate the salinity that we expect at different depths, or if you want to use temperature gradient, you can use temperature gradient. But the idea is that you can produce these curves for whatever basically liquid that you're throwing at this, and get an idea for what this ice is going to look like. So why is that important, right? So we have these ideas for the curves. We can match them up to the local thermal environment or your local depth. So we can start saying how much salt is in the shell in general. So you can just go through, you can do your integral on the constitutive equations that you produce. We say, why is that important? So on top of like a thermal convection, you could also have like a compositional convection, people have suggested. Bernie Schmidt's talked about if you have some kind of eutectic layer. So if you know, if you have a variation, some kind of thermal history that's going up and down, and you have a rapid cooling, that maybe you could get this eutectic kind of a layer, and you would be able to see that just using these constitutive equations by guessing how much salt you're going to trap in. So can you produce some kind of layer like that? Also, you can get estimates for if you have something extrude onto the surface, and the model's not excellent for extremely high temperature gradients, but once you build up anything, getting predictions for how much salt you can kind of like get frozen out in these melts. You can do the same thing with density, since it's just going to be related to composition. You could get density curves for the shell. Same thing, important for something like this. Brandon Johnson was talking about how you could have compositional heterogeneities as a driver for the subsumption, subduction, things like that. We can also apply it to different features. So we took some numbers that working with Catherine Walker for basically fracture geometries and modified the model a little bit to amplify the gravity drainage parameterization, since now you kind of have a more vertical instead of just a flat plane that you're freezing out. But you can come up and produce these same relationships for basically under a different thermal environment, how much salt you're going to trap in there. This is just the work that she had done relating basically the fracture geometry to the stresses in the shell. And so first, we looked at a basal one all the way down at the ice-ocean interface, and basically you can go through and produce what you expect the refreeze composition would be. And so obviously in a very turbulent environment, this wouldn't work, but if you can open up a crack that doesn't go all the way to the surface, and you don't have this kind of like plume dynamics going on, and it's somehow a little bit more stagnant and doesn't have as much convective turnover, then we can predict, and you have higher salinities by the edges that are going to decrease as you move inward.
What are we looking at?
Oh, sorry. So the idea here is that you're basically propagating a fraction, and the aspect ratio here is pretty high. So over here you've got something that looks like meters. So this is like a kilometer deep into the shell fracture, but it's probably only about 10 meters wide. These are the numbers that Catherine Walker came up with. So it's definitely extended. So in reality, it's going to be more like this dike propagation that's been talked about. And so you're going to have kind of more of a horizontal freeze-in as you go in. So this would be the resulting composition after it refroze. And then you can also do those for above these putative lenses. Probably. Oh, well, that's unfortunate. Okay. So, okay. One of the most important things we came up with is that there's, yeah. So there's a difference between the conductive solution, which people frequently use to estimate how long these liquid water bodies can last, and if you use this multi-phase model. So basically, this two-phase freezing front creates this thermal buffer that will slow down the propagation. And so if you go through and you measure, this is supposed to be the freezing front propagation versus time. And so the red dots are the conductive solution, just using a pure phase solidification as an analytical solution, and this is the model. And so the idea is that when you use these two-phase models, it's going to produce different results for your estimates of basically like residence times for these water bodies. This one unfortunately didn't show up either. This is freezing front propagation velocity versus thermal gradient. So you can do the same thing and you get a simple linear relationship. The values for this is you can go back to something like these fractures and you can use these estimates that relate the thermal gradients to the freezing front propagations, and you can come up with estimates for these crack reef closure times, something like that. The idea is that you can basically just apply these two-phase models to get somewhat more accurate estimates for freezing propagation times and compositional profiles. The last thing is that we're really trying to look at how to make these more and more accurate to try and get these estimates so that these kind of like high fidelity models can be used to produce some more constitutive equations for more broader concepts. So we really want to go to like a two-dimensional situation where you can kind of track the evolution of what's happening here and get more information about the fluid flow, how much is getting stuck in the ice, how much is getting expelled to the ocean. So instead of having to worry about parameterizations and things like that, actually modeling the whole two-phase system. I guess the last piece that's missing is kind of this relationship between porosity and permeability and relating, how much stuff can you actually expel, which is always kind of a difficult problem. That's it.
Okay, this is fantastic. But I apologize for sitting in the back, so I would like you to explain what did you mean by filtered? Like you had the Zolotov model and shock model, then a filtered Zolotov and shock. What does the filtering refer to? And you're imposing, I assume, this is basically a freezing front, and you're assuming there's a background heat flow that can vary. I mean, you can pick different ones. So, and my real question is, when the shell gets beyond a few hundred meters, if I could read the graph correctly, into the kilometer range, how saline is the bottom ice going to actually be? That kind of thing.
Yeah. So the filtered stuff was really just taking out early on, right when you turn the models on, there's some ringing. It's just numerical dispersion. So that was really just taking out some anomalous, probably first 10 data points on something that had 300 data points or something like that. And so the idea is that you have this background heat flux at the top that's basically creating this propagating freezing front. And it will asymptote, right? Like it goes to a minimum, and it's really set by this critical porosity. And so until we understand the critical porosity and how much you can actually trap in there, I don't think you can't know the lower boundary. I think there definitely will be one, but we don't know it yet. And there's still not a perfect permeability porosity relationship for like sea ice models. And so I have a paper on sea ice stuff where I've used a bunch of different ones, and you can get different results, but eventually you'll asymptote to something that's dependent on if you say that there's a cutoff.
Yeah, this is very important for our radar propagation models for Clipper.
Hi, really interesting talk, thanks. I just had a question about basing things off of sea ice and how confident you are in using that as your basis for the models when we don't really know that, the way ice is forming on Europa is going to be forming in the same fashion that it is here.
Yeah, are you concerned about like pressure mostly?
Well,
or
just
chemistry?
in terms of the porosities and how they form and permeability then as well. And sea ice, forms and reforms. It has snowpack on top of it, as it's forming year after year, or melting and reforming. And and pressures are different, temperatures are way different. Just the structure of the ice, and then how that would affect, the porosity and the salt retention or transport kind of stuff.
Yeah, I think it will definitely be more muted, just because things will probably happen on a lot longer time scales, like you're saying, and at different pressures. There's some places underneath ice shelves where you have like pretty much comparable pressures to Europa, if you assume like a 10 to 30 kilometer thick shell or something, where there's actually sea ice that grows there, and that sea ice is definitely a lot more pure. It forms a lot slower. You might have like a few meters over a couple hundred years. So there's some measurements from ice cores from that, which might be a little bit more applicable, and that's definitely more pure, holds less salt, but still has a salinity signature and things like that, and has like a columnar sea ice texture. But there's still, definitely some unknowns that need to be figured out.
Jeff had a question also.
Thanks. It looked like in the dike refreezing models that you had, I couldn't quite tell from the colors on there. It looked like there was maybe more salt trapped toward the top of those refreezing dikes than toward the bottom. Is that right?
Yes, yeah. So that one's definitely not perfect, and I think like moving to a fully 2D model would be a lot better with that. So that was definitely kind of like more of a toy application to say, like we can produce a quasi 2D profile even though it's a 1D model. So that was saying we're assuming like a horizontal freezing front propagation.
Mm-hmm.
But still using the geometry. So it's kind of a cheat there, right? Where I'm saying, there's a modified drainage property due to the geometry, but I'm still saying they're almost parallel, so that I'm just freezing them in.
Yeah.
So then you end up with this kind of like, just since there's there's more trapped at the top just because it's smaller, but if it's like pretty much on the edge, it will be the same moving in.
Yeah, I was just thinking about the earlier conversation today about all the dikes that don't make it to the surface, and how much salt do we trap up in the ice shell. I think sort of really nailing down that model and then figuring out, like, if we have lots of dikes that don't get all the way to the surface, how much salt do we get up in the ice shell would be really important problem.
Yeah.
I just have one really quick question. The chart you showed that showed there was a different residence time if you considered just conduction versus your model. What was the difference in order of magnitude for that?
So so we're doing stuff now finally with the model. We're taking it and trying to apply it to like these lens freeze out models or something like that. But the error will go is the square root of time. So it'll get worse and worse actually the farther you go.